In this video, we're going to talk about the Pythagorean identities as well as the periodic behavior of the trigonometric functions. So for the Pythagorean identities, we should really start out with a squared plus b squared equals to c squared. Again, that concept of leg squared plus leg squared equals the hypotenuse squared. And then we're going to go ahead and devolve into the concept of the unit circle by evaluating what a, b, and c are. Well, in this case, for using the unit circle, my hypotenuse c is always going to be 1. And for my a and b, based on the original way I set up the triangles, are going to be x squared and y squared. Now, this is the definition of how, again, the triangle in the unit circle, if I draw it really quickly here, there's my x, there's my y, there's my 1. But we also have to remember that in the unit circle, if we're playing with a unit circle, the definition of that point is also cosine of theta, sine of theta, which means that we do have a way that we can rewrite this identity into a Pythagorean identity. Again, utilize this rule into an identity that we can have a relationship between sine. Again, x is this cosine instead, so cosine squared. We have sine theta quantity squared equals to 1 squared. So now we have a rule that compares cosine and sine. Now, I'm going to be very specific about how I rewrite these things, because I put the parentheses around this. Keep in mind that theta is not what's being squared. It's the entirety of this function that's being squared. So what we're going to do is we're going to rewrite the cosine of theta squared as the cosine squared of theta. This notation is extremely prominent in the way that we write trigonometric functions. If the power is supposed to be on the entirety of the function, then we're going to put the power here next to the cosine, such that it's cosine squared of theta. Now again, it's the same concept as what's written here, but it's better to write it this way so that we don't necessarily have to write those parentheses like I did in this particular case. This is still sine squared of theta, such that it's sine of theta, where the whole thing is being squared. So this is your first Pythagorean identity, and it's probably the most prominent one that you'll see and recall. There are two other Pythagorean identities, such that if I were to take this original function, cosine squared of theta plus the sine squared of theta equals to 1, and I were to divide each piece by, say, let's start with the cosine function. If I were to divide each piece by cosine squared equals, again on both sides, again the whole side of this function divided by cosine squared, the cosine squareds here are going to cancel out, leave me with 1, plus, if I recall, sine over cosine by definition is tangent, but since it's sine squared over cosine squared, it's really sine over cosine all squared, which means that this is nothing more than tangent theta all squared, which again, I'm going to move that squared back into here because that notation is more appropriate. The same concept with this, 1 over cosine squared is really just secant squared of theta. So my second Pythagorean identity is going to be 1 plus tangent squared is equal to secant squared theta. What I'm going to go ahead and stop and say here is that the next few things that we're going to do when it comes to trigonometric identities is we're legit just going to play with them. We're going to specifically say, hey, look, this is what I know is true about sine and cosine. What else do I know? Well, this is then what I know is true about tangent and secant based on the fact that I know this to be true. Now, based on the fact that I know this to be true, there's one more thing that we can do is in this original identity, cosine squared plus sine squared equals to 1, we can manipulate, instead of dividing by cosine squared, we can divide everything in here by sine squared, and come to the conclusion that, well, this piece here in the middle is going to be 1, because sine squared divided by sine squared is 1. This piece over here is going to be my cotangent squared theta, and 1 over sine squared is really just going to be my cosecant squared function. And there, again, is another trigonometric identity that is specifically labeled as a Pythagorean identity. Because, again, the way that it works is I have something squared plus something squared, technically that one is squared, equals to another thing squared. So this allows us to manipulate and work with the trigonometric functions in another way. We're going to end up seeing these things come around a lot in the next couple of units. The last thing we're going to look at in this video is periodic functions. Now, if again you've already watched 4.4, video number 1, you already understand that the unit circle is cyclical, meaning that the unit circle repeats itself over and over and over again. We can plug in an infinite number of values for theta to every single one of these trig functions, and eventually it will start repeating itself. So the question is, for a periodic function, when does it start repeating itself? Well, what we're trying to say here is, in the general form, is that f of t plus p is eventually going to equal back to f of t before we added a p-value to it. So what functions have what kind of periods? Well, we can go ahead and start with a period value of 2 pi. We're going to start there. That period value of 2 pi, the functions that are going to have that period are sine of theta, cosine of theta, and again, their reciprocals. So cosecant of theta and secant of theta. What that means is, in the general form, that the sine of theta plus 2 pi will be equal back to the sine of just theta. So as I get past the value of 2 pi, this is for radian measure, or the value of 360, I'm going to just start repeating values that I've already seen in the original 360 degrees of the trigonometric functions. This is also true for cosine. I'm not going to write the other ones for secant and cosecant, but hopefully you guys get the point that I'm just going to be cyclically repeating myself for sine, cosine, secant, and cosecant in regards to 2 pi. Now this rule changes. What happens, however, if we're talking about tangent and cotangent? Well, if you look at the unit circle closely and carefully, there comes a point where the function starts repeating itself for the division of the x and the y value after only half of the circle. And it's because of the way the circle is built. Keep in mind that this is a positive positive. This location here is negative positive. This location down here is negative negative. And this location over here is positive negative. And you'll notice that if we start plugging in these values to divide them by each other, positive positive becomes positive when we divide them by each other. So does negative negative. And again, these two correlate. So I have a set of values on top and the set of values on the bottom. If I'm dividing the x by the y or the y by the x, they repeat themselves. They actually end up being the exact same values. So when we talk about the period of a value of pi, the two functions that correlate to that are tangent and its reciprocal function cotangent. So if I write this one down for at least just one of them, theta plus pi starts repeating itself in regards to tangent. So this is the main concept of how these functions are going to work, and these are the properties we're going to have to remember. Not only the Pythagorean, but the reciprocal, the quotient, the domain and range, and the periodic values. These particular examples probably don't come up as often as you'd expect, but it does help for us to memorize those concepts, especially in regards to the unit circle.